Okay, this will hopefully be my last video on the twin paradox. This is video 4. Just got to clear up a few things that I didn't explain properly. For example, that 80% of the time Alice is getting red-shifted wave signals from Bob. That's because even though Bob's turned around and started sending blue-shifted waves, she's not going to receive those straight away because she's not changing direction. She's not going to receive those until he's 80% through his trip. So that 80% has got nothing to do with the L, which is 0.8, which is the length contraction. That was just a coincidence, but I'll just try and demonstrate here. So let me put in a circle for the velocity, which is 0.6. Right, so I'll just go x squared plus y. Now I would normally just say y squared equals the velocity, the radius of the velocity. So there it is, but it's actually yellow, should be yellow, so it's there, and it's in the wrong place. So, but I knew it was going to be in the wrong place, so I knew I'd have to subtract 1. Now it's in the right place. Okay, now let's make the velocity 0.6, and this is the point in the trip where Alice starts receiving blue waves instead of red waves. See, it's 1.6, you halve that, you get 0.8, which is 80%. So 80% of the time she's getting red shifted, and 20% of the time she's getting blue shifted. Now let me up the velocity, and you'll see that I've upped the velocity, and now you can see that for 1.83 divided by 2 is a lot bigger percentage of the time that she'll be getting the red shift, whereas Bob will still be getting half red, half blue. So the difference in their times will just increases and increases until eventually she's not getting any blue shifted waves at all. Okay, now that explains that one, hopefully. Get rid of that. And the other point was I was going to show the other explanation which is given, which is to do with a virtual gravitational field. So to do that, I'm going to have to draw on that split view. Where is it? Here. And I'll just use better get that one, and I want to edit it and get my pencil thing out. Okay, so just to finish off one point, when Bob's moving at a constant velocity, it's like this velocity has been slowly increasing, and then it just started dropping again. So it's as if he went from here all the way to here to Alpha Centauri, because when you calculate the distance, it's actually 2 times this little amount, which is gamma minus 1. So it's that one plus that one, and gamma minus 1 is relativistic kinetic energy, the factor for relativistic kinetic energy. So you see you've got this circle there and that circle there, and then you've got this little bit here, and that's the distance he's travelled. And I've also got to make the point that there's got all these constants out the front. If you remember, I had the speed of light, which is 300 million meters, and then I had his acceleration, constant acceleration, which was 9.8 meters per second. Then I had this number, which is actually the number of seconds in a year. So these are just a bunch of constants, all designed to sort of fix the units, and that's velocity over acceleration, which is time. 2, because that would be 1, that would be 2, that would be 3, and that would be 4. So they're all. So 1 is then the mirror image is 2, and then 3, and then 4. But all of these 1, 2, 3, 4s, they all create the same amount of time difference. So you just go, if you wanted to do a return trip, which would be there and then back, you'd go 4 times these constants, and then the factors, which would be gamma plus the log of that, which would be the accumulated time for Bob over that, which would be the accumulated time for Alice. Okay, anyway, hope that's clear as mud. So, but I wanted to get on to the explanation, which is often given, which is that there's a virtual gravitational field. So this, hang on. So I said that distance is L, that distance is 1, that distance is T. Well, that distance from there to there is actually L over T squared. So that's acceleration, isn't it? And it's actually centripetal acceleration. There's another one here, which is L over T cubed. That's actually tangential acceleration. And then there's this one here, which is actually proper acceleration. And that's usually given as the reason for the this virtual gravitational field. But I would say it's centripetal acceleration because it's in line with this gravitational field. And what happens, so here's Bob accelerating, and because he's accelerating, he's expending energy. And so the equivalence principle says that that's the same as a gravitational field. So he's standing here feeling a gravitational field because he's accelerating, and that means he's in a virtual gravitational field, and therefore the signals coming from Alice are dropping in a gravitational field, so the actual frequency's increasing. So it's because it's dropping in a gravitational field, according to him, it's increasing anyway. So that's what he's seeing. He's seeing an increased frequency from Alice. So that's why more time is passing for her from his point of view, apparently. Yeah, so that's the reason given with respect to a virtual gravitational field. But there it is on the graph. Is that enough? Yep. That'll do. Actually, I'll just finish off this. Now, what is that length? It's actually L times T. So, because Einstein just said that a time dilation is due to gamma, which is that length there. He didn't bother with this length t, but he had to explain the gravitational field, so he had to come up with general relativity, and so he had to include space-time, and the equation for general relativity is that space-time is equal to the square root of t squared minus L squared. In other words, time minus space. So you can see it's just a right angle triangle. So that's just Pythagoras theorem. So that's his reason. Then he would say that there's curved space-time because of this, because space-time is actually curving down and creating this gravitational field, as well as length contraction, and time is slowing down as well because t is getting shorter and shorter. And of course, Alice's, the clock on Alpha Centauri, which is in Alice's frame, because that's not moving with respect to her, so this is her clock really, is actually dropped in this gravitational field according to Bob, so its time is actually moved ahead by 0.6 at this point, 0.6 c, 0.6 units of time, let's say. So her clock is moved ahead, but there's still got the symmetry because according to Bob, Alice is moving with respect to him, so therefore her clock must be running slow, and it is LT. That means her time is only 0.8 of his time, but he's thinking of this length here. But so he's right in a sense, but to get to Alice's total time, you have to add this one to that one, and so you get her total time is actually from there to there. That's why more time passes for her, because although her clock has moved ahead, the clock in front of him has moved ahead by 0.6, it's actually running slow relative to his clock. But you add the two together and you get a greater time than his time, because his time is that. But the time difference is always gamma, and that's why Einstein said the time difference, all you need is gamma to calculate the time difference. But look at gamma, there's no t in there at all. It's actually a unit of space. 1 over L is just a unit of space, so it's actually the space in the other frame. So its space is contracted in the other frame, but is not contracted, well, it's dilated, you could say, in the other frame. And if you were to add the two together, gamma plus L, you get 1. In other words, space is constant. Yeah, so in a way, a clock running slow, you could call that special relativity really, and the clock has moved ahead due to a gravitational field, you could call that general relativity. So so it's like you're adding a bit of general relativity to special relativity to get Alice's time. Anyway, that'll do.